In this segment, we're going to talk about sampling from a stream. So we're going to assume that our stream has distinct items. This is not essential, but it helps to keep the problem clean and simple. So we have a stream of some n items that are showing up, but we don't know n. Our goal is to sample from the stream so that we output an item from the stream, and the probability that each of these items is output must be equally likely. So in other words, for all I, the probability that AI is chosen must be 1 over n. And so this, without the knowledge of n, is somewhat tricky. But as it turns out, there is a nice clean way to sample from a stream. And here's how this algorithm goes. We have a memory cell, a single cell, because we want to sample a single item. And let's just call that S. S is initialized to bottom. So initially, S doesn't have anything useful. And now let us see how we update S as the stream flows by. So every time we look at the ith item, we toss a coin with bias 1 over I. And if that coin comes up heads, in other words, with probability 1 over I, we replace the current contents of S with A sub I. And of course, A sub I is the ith item. Okay, so now, and that's it. This is the algorithm. We need to now prove that this algorithm actually outputs the correct sample that we want. In other words, at the end of the stream, when all n items have been seen, the probability that the memory cell S contains AI should be equal to 1 by n, and this must be true for all So now let us go about proving that our algorithm, the reservoir sampling algorithm, is in fact correct. So how do we do that? Let's look at the probability with which the ith item is finally output. Okay. First of all, the ith item must have had a chance to get, must have gotten into the memory cell, and that at the point in time when the ith item has been seen, the ith item gets copied into the memory cell with probability 1 over I. And furthermore, if the final outcome must be the ith item, none of the subsequent items can replace I. Because once it's replaced, it's gone. That's the way the algorithm works. So what's the probability with which the next item, the I plus 1th item, does not replace the ith item from S? It replaces the ith item with probability 1 over I plus 1, and therefore it does not replace the ith item with probability 1 minus 1 over I plus 1. And this same pattern has to continue. The I plus 2 at the item also should not have replaced item I. We get these this sequence of multiplicative terms. So let's see how this multiplicative terms how they expand out. As it turns out, they have a nice form. When we expand them out, it's a sort of a telescopic product, and most of the terms cancel out. And we're finally left with 1 by n. And this is, of course, true for all I, which is exactly what we wanted to prove. Let us now move on to sampling not just one item, but some k items. Here we need to be a bit more careful. Now, this sampling can be done in one of two ways. We can either sample with replacement or without replacement. Now, with replacement is somewhat straightforward. We can simply perform k independent reservoir sampling for single items. So that's relatively straightforward. Let us now come to the aspect of sampling without replacement. So now, if you consider any subset of k items, it should be equally likely. That subset should be picked with equal likelihood as any one of the n choose k possible such k item subsets. So how do we do that? Well, here we again rely on the previous intuition from reservoir sampling. We just need to be a little bit more careful. This is quite intuitive. Here's how we do this. Instead of maintaining one memory cell, we maintain k memory cells. These k cells are denoted S1, S2, and so on up to Sk. And for the first k items, you simply assign the item ai, I ranging from 1 to k, to the memory cell Si. Now, what happens if I is greater than k? We first generate a random number, and this random number is generated uniformly at random between 1 and I. And if that number, the randomly generated number, happens to be between 1 and k, then we replace the jth memory cell. So the random number, if it's less than or equal to k, that means it's the j is Sj is somewhere here, and we replace the contents of Sj with ai. That's what we do here. So let me give you a little bit of intuition for why this works. Now, the first k items, we have to fill them in because if the stream stops at k, there is only a single k item subset, and that must be the subset that is output. Now, as think of this, think of the stream as extending past these first k items, and consider the item ai. With probability k over I, so this is k and this is I. With probability k over I, it replaces an item from the memory cells. And which memory cell should it replace? It replaces exactly the index that was generated randomly. So why is this algorithm correct? Or actually, first of all, what do we need to show to say that this algorithm is correct? So first of all, notice that this algorithm is going to produce a subset of k items. It's not with repetition. So that part is taken care of. Now, what we want to show is that the probability with which item ai occurs in the chosen subset is k over n. So more formally, let S be the set of items that we output as the samples, basically the contents of the memory cells when we reach the end of the stream. Now we need to show that the probability with which an item ai is in that set S is equal to k over n. So how do we show that? Well, first of all, the item ai must have been placed in the in one of the memory cells, and that happens with probability k over I. And then it should remain in the memory cell in which it was placed. So let us, without loss of generalities, say that the memory cell was placed in some particular location. The I plus 1th item should not have fallen in that particular location. Well, the I plus 1th item falls in that particular location with probability 1 over I plus 1. So it does not fall in that location with probability 1 minus 1 over I plus 1. So let me go back to the picture to explain exactly why this happens. So let us assume that the ith item gets placed in this cell Sj. Now the I plus 1th item can will also generate a random number. If it generates the random number anywhere here, no problem. If it generates a random number that falls within this range, well, we need to be a bit careful. If it falls anywhere in this region, that's okay. If it falls anywhere in this region, that's okay. The only location that should not fall into is Sj, because if it falls in Sj, then our item AI has to be evicted. And so the probability of that is 1 over I plus 1. And therefore the good probability, the probability that AI gets retained, is 1 minus 1 over I plus 1. And of course this has to be maintained throughout, so you get a similar telescopic product which finally will evaluate to k over n, which is exactly what we wanted. Now, as an exercise, think about this. What we have shown is that the item AI is one of the elements of the subset that we are outputting at the end of the stream with probability k over n. Does this translate to what we actually started out with? What we wanted was that the probability that any fixed k item subset is chosen as the subset that is output should be exactly equal to 1 over n choose k. So have we proven this? Think about this. That's your exercise. So that completes our segment 2.